Okay, so we are about to pose a question here, like what is the difference between a function being real analytic and being complex analytic? That is, what I'm trying to say is the notion of differentiability same in both complex and real? That is, suppose uh, we say a function if is is real analytic at a point x naught if power series expansion about x naught exists. That is, if x equals to a naught plus a1x dot 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 n x to the power n and so on, where x belongs to x naught epsilon x naught plus epsilon for some epsilon greater than 0. Now if we differentiate if we calculate f prime x, oh sorry, this is supposed to be like this. So if we compute f prime x, we see that it is a1 plus 2a2 x minus x naught dot dot dot. Compute f prime x naught, it is a1. If we compute f double prime x, we find it to be 2a2 plus 3 factorial a3 a minus x naught dot dot dot. If you compute this, you get 2a2. a2 is f prime x naught by 2 factorial. So inductively you have an is if n x naught by n factorial. That is, if x is summation n running from 0 to infinity if n x naught by n factorial into x minus x naught whole to the power n, where x belongs to x naught minus epsilon by x naught plus epsilon. So clearly, one thing you notice that if n x naught exists for all n belongs to natural number, so we get that. So maybe I should write like this: if is real analytic at x naught implies if n x naught by n factorial, I mean I should be writing if n x naught exists for all n belongs to natural number. we know that if is analytic, or maybe complex analytic I should write, if is complex analytic at x naught belongs to C, if and only if and we know that these two nations are equivalent when you are when we are talking about complex differentiation. Question: does the converse hold for if f is R to R? That is, let fn x naught exists for all n belongs to natural number. Does it imply that f has a power series expansion about x naught? The answer is no. Let's look at an example. So let ft is e to the power 1 by t, or maybe we should be looking at this equal to 0, 0 if t equals to 0. You see that f prime 0 will be fh by f0 by h limit h tends to 0. So it looks like 1 by h, this is 0. We can show that if n 0 is 0 for all n belongs to natural numbers, but if has a power series expansion about x not equals to 0, then fx is f0 plus x into f prime 0 plus x square into f double prime 0 by 2 factorial and so on. That is, for x belongs to minus epsilon to epsilon for some epsilon. So then we get e to the power minus 1 by x square is basically, see, if 0 is 0, if prime 0 is 0, and everything here is 0. So we get that the whole RHS is 0, but clearly this term is non-zero if x not equals to 0. So LHS is not equal to RHS. This means that the power series expansion of this function about 0 doesn't exist. So this shows that if f is smooth at a point, that is, if every derivative of x exists at some point, doesn't necessarily mean that f has a power series expansion at that point. So here is the power of complex differentiation, that it is if and only if when we are speaking about the complex plane. Let's see some definitions of convex and concave functions. It is like